In this next chapter, we're going to be focusing on determining the behavior of a function on an interval I. So we're going to talk about maxima, minima, increasing or decreasing behavior, concavity, all these different things, and how we can use the calculus that we've learned so far to answer these kind of questions, and eventually talk about how to get a sketch of a graph of a function based on this information. So the first definition we have here is what are called extrema. So if we let f be defined on an interval I containing a number c, f of c is said to be the minimum of f on the interval I when f of c is less than or equal to f of x for all x in I, and f of c is the maximum of f on I when f of c is greater than or equal to f of x for all x in I. So we're talking about on an interval I, and remember I is a subset of the domain, the maximum or the minimum is the highest or the lowest y value of the function on that interval. So we say that the minimum and maximum are the extreme values, or you might see this called the extrema of the function on the interval. And the singular form of the word extrema is said extremum, like that. Now, one thing that's important to understand is that the minimum and maximum of a function on an interval are also called the absolute minimum and maximum, and the absolute maximum. Or you might see them called the global minimum or the global maximum. These are the highest, absolute highest or lowest values on the interval. Now, a function does not necessarily have to have a minimum or maximum value on an interval. So there may be some cases where the function goes to infinity or negative infinity and it doesn't have a highest or lowest value. So that's perfectly legitimate. And one thing that you also want to note is that extrema can occur at interior points or on the endpoints of an interval. And extrema that occur at the endpoints are a special type, so they get their own name. They are the endpoint extrema. Very descriptive. So this is some cases of what this could look like. In this picture right here, you've got an interval from -1 to 2, and notice that the maximum here is an endpoint extrema or extremum, and the minimum is just an interior minimum. So that would be the minimum value and the maximum value. In this case, you've got a minimum value here. You have an open circle on the point 0.25, so this is actually not a maximum, and this particular case does not have a maximum because that point is getting closer and closer and closer to the point 2,5, and you don't know, there's no actual highest value. It just keeps getting closer to that. In this case right here, you do have a maximum at 2,5, but you do not have a minimum for this graph for the same reason. That open circle means that it's not a minimum on either side. It's going to get closer and closer and closer to that y value, but it's never going to actually touch it. As you saw in the previous example, continuity is one thing that can definitely affect the existence of a maximum or minimum on an interval. So this theorem is the first theorem of chapter 3, and it's called the extreme value theorem. It says if f is continuous on a closed interval AB, then f has both a minimum and a maximum on the interval. Now, one thing that's important to notice is that this is an existence theorem. Just like the existence theorems we've talked about before, it only tells us that a value exists. It doesn't actually help us find the value. So if you know that it's continuous on a closed interval, you know it has both a minimum and maximum. You just don't necessarily know what those are. You don't know whether they're interior or endpoint extrema as well. So you know that they exist, but you don't know any information about them yet. Now, in contrast to absolute extrema, we also have the concept of relative extrema. This says if there is an open interval containing c on which f of c is a maximum, then f of c is called a relative maximum of f, or you can say that f has a relative maximum at the point cf of c. And if there's an open interval containing c on which f of c is a minimum, then f of c is called a relative minimum of f, or you can say that f has a relative minimum at cf of c. So when we talk about relative maxima and minima, we're talking about those high and low points. They don't have to be the absolute highest point on the graph or the absolute lowest point on the graph, but on some interval, they would be the highest or lowest. So let me show you an example of what that could look like. If we look at this function, we can see that this function has no absolute maxima or minima on the whole interval, because if you look here, it's going to go down forever towards negative infinity on the left and up forever towards negative infinity on the right. So it doesn't have any absolute extrema on the interval from negative infinity to infinity. However, it does have some high and low points. So if I'm looking at this point right here on the left, if I were to draw an interval around it, I could see that on that interval, that point right here is the highest point. Okay? Similarly, I could do that for this point here, and I could see that on a specific interval that's a subset of negative infinity to infinity, that is the highest point. So these points that I've marked in red would be relative maxima. Okay? And similarly here, you can see that on an interval around that point, this would be the lowest point, and the same thing here. So these points that I'm marking in green would be relative minima. And even though you have this point higher than this point, these are each relative minima, they're minima in their particular region, you can actually have, maxima. So even though you have this point is obviously higher than this point, both of them are considered relative maxima because on their little corner of the world, or in their little corner of the world, they are the highest point. It's actually possible to have relative minima that are higher than some of the relative maxima on the graph. So they don't have to be maxima or minima in relation to each other, just in relation to the points around them. And for this reason, relative maxima and minima can also be known as local maxima and local minima. So we can see from the graph of negative x squared plus 4x plus 5 that f of x is a relative maxima at the point 2, 9. This is the vertex of the parabola that is this graph. So what we're interested in is what is the value of f prime of x at this point. So if I find f prime of x, that would be negative 2x plus 4. So if I plug in the x equals 2 from the ordered pair, I would have negative 2 times 2 plus 4, which is negative 4 plus 4, which is 0. So in this case, my derivative is equal to 0. And it turns out that this is not a coincidence. At each relative extremum, the derivative evaluated at that point is either going to be equal to 0 or it's not going to exist. So we call any such x value a critical number. So this is the definition of a critical number. We're going to let f of c be defined, or we're going to let f of x be defined at c, and if f prime of c is equal to 0, or f is not differentiable at c, then c is a critical number of f. You may see these called critical values as well. It means the same thing. So critical values or critical numbers are values of x where something is going to be happening at that point, and it's either going to be an extrema or it's either going to be a relative minima or maxima. So let's find all the critical numbers of a couple of functions. So the first thing that I want to start with is I want to find the derivative. So f prime of x here would be 6x squared plus 6x. Now this is a polynomial, so it exists everywhere. We don't have to worry about where the derivative does not exist. We only have to worry about where the derivative is equal to 0. So I'm going to set 6x squared plus 6x equal to 0. To solve that, I would factor out a 6x, and I get x plus 1. So 6x equals 0, which means x equals 0, or x plus 1 equals 0, which means x equals negative 1. So my critical numbers for this function are going to be 0 and negative 1. Looking at this example, I'm going to take the same exact approach. I do want to write this as x to the 1/2 power before I begin because that's easier to find the derivative of. So f prime of x is going to be 1/2 x to the negative 1/2, or 1 over 2 square root of x. We found this derivative a bunch of times now, so if you don't remember, make sure you take a look at it. So one thing that is important to note is that f prime of x does not exist at x equals 0 because that would make your denominator equal to 0. So that's one of our critical numbers, okay? So we want to know if f prime of x can even be equal to 0. So can 1 over 2 square root of x be equal to 0? And the answer here is no, because your numerator is 1, and if your denominator equals 0, it doesn't exist. So in this case, the only critical number is 0. Now there may be some cases where you get critical numbers from both situations. Normally it will be one or the other, but it could possibly be both. So don't neglect one or the other. Now the reason that we are interested in critical numbers is that critical numbers are our only candidates for relative extrema of a function. So relative extrema are only going to occur at the critical numbers. If f has a relative minimum or maximum at x equals c, then c is a critical number of f. Now notice, this doesn't say that critical numbers will be maxima or minima. It just says that they're the only candidates for maxima or minima. So it takes all of the possible numbers in the domain and narrows it down to just a couple, and that's a lot. That gives our chances of actually finding the minima or maxima gives us a lot better chances there. So that's where we're going to be looking.